So, we are busy with compressors and mainly looking at what I've called the surge margin. And the surge margin, this is a parameter that is expressed in percent that I have defined as at a given mass flow rate, of course we speak in corrected mass flow rate, is a difference between the pressure ratio at the level of the surge line and the pressure ratio at the level of the steady state line compared, because we want to have a non-dimensional value, with the steady state line pressure ratio. So I remind you what it is at the level of the compressor map. So the compressor map, this is something showing this with different speeds, isospeed curves, with the corrected speed increasing in this direction. And so we are interested by the position of the surge line that I show here, the surge line, compared with the steady state line. And we know that the steady state line is much inclined. It has a shape like this. This is a steady state line at a given Mach number, I don't know, Mach number 0.8 or something like that. We know also that we have the iso-TIT curves that are curves like this, with an increasing value of the TIT divided by the TT1 that is like this. And so what we call the surge margin is the value that you have here. This is this distance at a certain value of m dot divided by the value you have there. Of course you will say me, then this is much smaller here than there, because we see that the distance is decreasing and that this value is increasing. So we will have a much smaller surge margin here than there. That's right, but don't forget that the steady state line is a curve that is in fact something like this. So this is a curve that is in fact something like this, with the Mach number increasing in this direction. That means when you are at low engine rating, low rotational speed and low m dot, you are more compared to this curve and not compared to this one. So you see that it's this surge margin or this distance that you need to consider and not the distance compared to this point. So be careful with the, let's say, wrong interpretation that you could have. And so we are interested by this, and this is of course related with the position of that we have already studied, let's say, in the part 2 of the course, and also the position of this that you have most probably partly discussed in courses related to turbo machinery, but that I would like to remind again. Why? This is because we are most probably, on the contrary of what you have seen in your course of turbo machinery, we are speaking here about a compressor. That means a full compressor. So that means a compressor that is containing a certain number of stages, with the rotor 1 here, the stator 1 there, and the rotor 2 here, and here the rotor number, I don't know, F, final, and here the stator, that is the final one. And everything is of course rotating, in my understanding, at the same rotational speed. That can be N1, that can be N2, that can be N3, depending on the compressor that you are considering. But we are speaking about a multi-stage compressor. And in a multi-stage compressor, I think that you have most probably not studied what it is exactly from the point of view of the surge. And I have explained to you yesterday that the surge is in fact globally a phenomenon that you can call the stall. That means the boundary layer separation. The boundary layer separation, if you have a blade of a compressor, you have the direction of the cord, which is this direction, the direction of the cord. You have so a certain velocity triangle, so maybe that the absolute velocity is not axial. Yesterday I have represented an axial, maybe it's not axial. You have u here, you have the absolute velocity that is there, and you have the relative velocity, and you have the angle of attack here. And you want to work at the value of the angle of attack that is as high as possible. Why? Because the angle of attack is related with CL, and this is CL that makes the pressure ratio. The pressure ratio, the change in pressure, in total pressure that you will have on the blade will be related to CL. So you want to work in this region. And in fact, if you are here, let's say, in this region, you see that you will be very quickly on the other side of the problem. And at the other side of the problem, you can have a decrease that is like this. This is what I have called a trailing edge separation. That means that the separation is starting from the trailing edge. Or you could have, of course, most probably not with the same profile, but here I'm representing that like this. You can have something like this. That would be a leading edge separation that is much more abrupt, much stronger than the trailing edge separation. And I have explained to you yesterday that in the case of the trailing edge separation, it depends, of course, what is the intensity of this trailing edge separation. You can have another phenomenon of stall that can exist, which is called the rotating stall. Whereas with the leading edge separation that is here, you will have a phenomenon that is also a stall, but that we call a surge. And I said to you also yesterday that we need also to speak about, let's say, a third one, if we want to be clear, that is called the stagnation stall, okay? And in fact, when you are speaking about a multi-stage compressor, this is important to mention that. Why? Because the difference, the fact that due to an incident, yesterday I spoke about an impact due to a stone, or it can be due to a bird, it can be a lot of things, icing for example. I will discuss today other phenomena. Depending on where you have the impact, if this is on a, let's say, long blade, or if this is on a short blade, so beginning of the compressor or end of the compressor, you will be more going into this direction, or you will be more going into this direction. Because the same impact has, let's say, a much smaller effect globally on the mass flow rate in this case than in this case, where the surface here impacted is much smaller compared to the total surface, because mass flow rate is related to surface, than what you have on one of the final blades. And so you see that discussing multi-stage compressor is important, because the problem can come from the first stages here, or can come from the last stages here, and it will not lead to the same type of problem. Here it can lead to a rotating stall, here it will lead most probably directly to a surge without the possibility, or in very rare cases, of a rotating stall. So studying a multi-stage compressor is very important. The people studying rotating stall and surge, they are very often studying that at the level of a single stage. So the understanding is difficult, and so they are concentrating on understanding the phenomenon, and they are studying that at the level of a single stage. And if you take a single stage, very often they will not represent the pressure ratio and the mass flow rate, but they will look more at the problem from the point of view of the velocity triangles. And if you remember well, in the velocity triangles, we are introducing, let's say, a force velocity triangle, which is the axial velocity. So there are three vectors, but there is also a fourth one, which is the axial projection of the relative velocity and of the absolute velocity. This is this one. That I call V axial. And you have U, that is here, and the angle of attack that is there. And when you are studying the problem from, let's say, a stage point of view, a single blade point of view, really concentrating on the aerodynamic problem related to stall, they are representing, in fact, the same as what we have done, but instead of taking the pressure ratio, they take the delta P, the variation of the pressure, total pressure divided by another pressure, and they will take 1/2 rho V square, which is a dynamic pressure like this. You have a variation in pressure divided by a pressure. This is non-dimensional. And in order to represent the mass flow rate, they take V axial divided by U, because V axial is proportional to the mass flow rate. By dividing it by U, you have, let's say, a kind of adimensionalization from the point of view of the rotational speed. And if you take a certain rotational speed, what is the type of curve you can obtain? You can obtain, in fact, two types of curves. So I'm trying to represent that adequately. So you can have a type of curve that will be something like this. That means that you can go over this point by looking precisely at the evolution of the flow, going very slowly from one point to another, decreasing and decreasing the mass flow rate, decreasing and decreasing V axial, and this is the way they are doing. You go from this point to a point that is there. Or you can have also curves. I will represent it at, let's say, another rotational speed, or I can represent it on the same, but it will be more difficult to visualize. You will have a curve that is in fact like this, that is going behind, something like that. So a different behavior behind this point, so in this region. And that will be closely related with the value of the type of airfoil and the value of H/C, which is the height of the blade divided by the chord, H/C, that is here large and that is here small. And if you